We'll move to the next presentation by Dr. Tom Lewis from Trie Engineering, and he's going to make a presentation on NOx control systems and how to ultimately achieve this NOx control while using Petcoke in the ILC and SLC plants without SNCR. So third generation NOx post processor. I request Dr. Tom to start his presentation.
Dr. Laws, you are on, please.
There we are.
Yeah. You can share the screen.
Yes, that's what I'm busy doing. Right. Can you see and hear me okay?
Yeah.
We can hear you,
You can
but
share the screen. You can share the screen, I think.
Shared it already?
Not yet visible.
Laws, could you please do that again? Could you please share your screen again?
Okay. Share content. Is that working okay?
Yeah, it's visible now.
Okay. So shall I start?
Yeah.
Okay. I'd like to introduce you this morning or this afternoon to how one can get 500 stack NOx emission with 100% Petcoke, an ILC or a separate line calciner using no SNCR by using really human intelligence and an advanced CFD. My co-author is Joanna Bretz, and really, why do Joan and I dedicate so much of our time to helping plants reduce their NOx emissions? Quite simply, in terms of toxicity, for the maximum exposed individual, NOx is the most toxic emission from a cement plant, with reference to the World Health Organization tolerable limits for 24/7 exposure. India has a high level of excellent low energy 5 and 6 stage preheating calciner plants. However, it also has some of the highest levels of NOx emissions in the world I have come across. And quite simply, why? It all goes back to the late 90s when Mr. Jaju, the then CEO of Grasm, walked into my office and asked me to tell him why his plants couldn't get above 25% Petcoke without jamming. I explained my technology, and within a week I was in Aditya, followed by Vikram, working with them over a couple of years, supported by Mr. Jaju, for both investment and team efforts. They got to 100% high sulfur Petcoke, which is then replicated to other plants and generally followed by some other companies. Many plants in India have high Petcoke, use of which is a very high NOx producer, particularly in separate line calciners, of which there are many. So how do we fix it? Typically, you need first to understand the real fundamentals of NOx and generation and destruction in cement plants, and then apply them in an optimum low-cost way without resorting to SNCR. While the NOx generated in the kiln is important for responsible up to 40% of the stacked emissions, these are readily controllable via calciner optimization. Hence, knowledge of how NOx is generated and controlled in the calciner is of paramount importance to getting the stack NOx down to less than 500 at the stack without SNCR. Typically, NOx and calciners can be constantly generated solely from the fuel nitrogen. Thermal NOx cannot be produced at temperatures less than 1700 C, and prompt NOx, if generated, is small. Typically, a simple schematic adequately explains it all. The nitrogen in the fuel during heating and combustion evolves to volatile nitrogen and char nitrogen. The volatile nitrogen goes to HCN and ammonia, and the ammonia then reacts with oxygen to produce NO, and the HCN reacts with oxygen to produce NO. Or if one has substoichiometric conditions, the HCN and ammonia will react with the NO to produce nitrogen. If in the situation where you have substoichiometric conditions, you have CH radicals or hydrocarbons, they can react with the NO, what's called reburning, to return it to HCN, which then, if there is a paucity of oxygen, which is really substoichiometric reburning, they will react with the NO to find the nitrogen. The char is potentially a problem area on Petcoke and low volatile coals, not so much a problem for the normal bituminous type coals and even AFR. The char nitrogen, when it's evolved, will react with oxygen to produce NO, or react with NO to produce nitrogen. And with high specific surface area char, the contribution of char nitrogen to NO is around about 10%, but with low specific surface area char, typically of low volatile coals, you get a huge conversion of char nitrogen to NO, and that's the problem you have in India with your Petcoke. Typically, the fuel nitrogen for coal is between 1 and 2%. With AFR, can be 0.5 to 3%. Generally, AFR has higher fuel nitrogen, but comes with higher volatiles, and therefore can more readily be reduced to nitrogen. Typically, is it possible for me to take this off the screen? Okay, so typically you see here a coal with 30% volatile, 0 reburn, 0 staging, only 10% NOx from the char. You get a typical emission of over 1100. With 80% reburn and 50% staging, still only 10% from the char, you can get down to less than 500. But when it comes to Petcoke, typically you have this high amount of char nitrogen, char NOx that's formed, that takes it to 1400. And then you need to be able to work out how to reburn and stage it and reduce the amount of NOx coming from the char. And you can get down to less than 800. For a separate line calciner, less than 800 is not possible without fuel and meal staging, because air staging without an extra TAD or the use of coal or AFR as a hot reburn. It's this technology associated with reburn and staging and getting less of the char NOx formed is the basis behind Trie technology. Somehow so to get less than 500 without AFR and SNCR requires luck or good reburn design, either in the plant build or retrofit afterwards. The concept of reburn is not new. It was developed by Mikko Hooper and applied by Joan and myself around about 10 years ago, and it's within the embedded paper in the conference proceedings, the IEEE paper. Basically, to get a hot reburn, typically we go for 1300 degrees centigrade for 0.15 seconds, followed by 0.5 seconds before the TA, with low meal addition for a customized retrofit for calciners, for stoichiometric ratio for the volatiles of less than 0.9. Typically, to further react to form nitrogen and oxygen to reform NO, the next slides show how important hot reburn temperature is. Here you can see if you have a hot reburn in around about, say, kiln back end oxygen of 3%, if you minimize the amount of lower meal and hot reburn round about 1300 degrees centigrade, you can reduce your kiln back end NOx from 1000 to 200 ppm with our hydrocarbon radicals around about 0.15 seconds. However, you need then to convert the HCN to NO by reacting to HCN to nitrogen by reaction with NO. And here you see that you need to not quench it too fast with meal, because you need to have the order of 0.5 seconds at 1050 degrees centigrade and even lower at higher temperatures. So consequently, depending on the residence time that's available below your tertiary air duct, you have to adjust the temperature appropriately to get the level of hot reburn that's required. Typically, you see some planned data here with and without hot reburn. This was a typical coal-fired installation where you can see the stack as a function of the kiln back end NOx has a fairly steep line with an inclination of 0.32 and 0.29. Typically, that shows that there is an impact of the kiln back end oxygen on the stack of 0.32 or 0.29 factor. If it was complete pass-through, the factor would be 0.4. Here you can see where the hot reburn through burner optimization and moving the burners down within the calciner drops the factor to 0.12, and also the amount of NOx formed from the coal in the calciner drops from the 500 to 600 down to 294, and you have a reburn of 73% and staging of 50%. This is the basic technology that we use to drop the kiln NOx. If there was complete reburn and no impact of kiln back end NOx and stack NOx, this line would be completely horizontal. So when one looks at the plot of stack NOx, kiln back end NOx, you can see already what's happening in your calciner and on your stack NOx in terms of reburn and calciner fuel NOx generation. Basically, this shows a typical FLS calciner where one has dropped the NOx significantly by ensuring that the hydrocarbons don't burn out too fast and reburn the NOx going all the way up until the tertiary air. The total residence time is 0.65 seconds, but the burners are designed down here to give 0.15 seconds before 15% lower meal. So typically, the schematic for a hot reburn with fuel nitrogen stage in an inline calciner would be 2 injectors designed for 1300 C with 0.15 seconds before the lower meal to reburn the kiln back end NOx by at least 80%. Right. Then the lower meal 0.5 seconds below the TA duct with meal 15% maxed, allowed to design at least 1000 C to allow fuel nitrogen staging. Then TA duct 0.7 seconds above the injectors, and the remaining meal a meter above the TA duct to avoid too rapid a quenching and allow the calcination to occur. And depending on this particular geometry on any particular inline calciner, you then customize the burners, the injector position, how much meal you use, to get the required residence time and quenching as a function of the distance below the calciner. When it comes to South African coal and anthracite, hot reburn doesn't work quite as well. And the main issue is that the fuel nitrogen in the char stays high and causes particular issues. Here you can see a typical plot of stack against kiln NOx for a South African coal-fired FLS type calciner, and you can see here the high levels of char NOx that is generated, and you have a stat NOx of 960, 996, and when we take off the lower meal, it's still 826, and the guarantees is for 600. The balance shows that even with the lower meal off, you still have a huge amount of char NOx formed from the char nitrogen. So consequently, to get that less than 600, you need to completely lower the burners to as low as possible and turn off the meal. And that can sometimes give rise to too high a temperature. Therefore, one needs to turn back the calcination to around about 90%. The next shows a bleached calciner, 500% Petcoke, right? And here you can see where you are running at around about 1,094. My estimated calculations are that the kiln NOx reburns 45% from this gradient on the kiln back air NOx, but you still got a huge amount of NOx coming from the fuel in the calciner, which is the Petcoke. So consequently, to drop the NOx from that, you need to look at air staging. And air staging is essentially where you put in an extra tertiary air duct and run at a substoichiometry of around about 0.7 for all of the combustion. And consequently, you have the situation where you can really drop your NOx. And basically, how best to exploit it is that you need to reburn the kiln NOx for substoichiometric vols around about a maximum 0.9. Stage the volatile fuel NOx with substoichiometric vols, and then minimize char NOx by substoichiometric of the order of 0.7 for around about 1 second. For bituminous coals, we can potentially reach 200 milligrams per normal cubic meter at 10% oxygen by applying the above design for ILCs. And even for separate combustion chambers, you get as low as 500. The next slide shows modeling results for two-step meal for 100% Petcoke, which shows that the SLC can drop by 25% by doing it. However, it should be noted that you need a two-step meal to be able to do it. Basically, here you see how the NOx can be dropped from 1100 to 800 ppm using it's split Petcoke, 70% at the bottom, 30% at the top, but without splitting the meal, one got no drop in NOx. So consequently, for an SLC, fairly cheap, low-cost modification is to split the coal and split the meal, and consequently, you can drop your NOx by 20-30%. But basically, the base case is 1100. If you did not split your meal as well as your fuel, you got no drop in NOx. So consequently, for SLC and ILC, for a low NOx generic solution, is you need I'm not sure whether you can see this diagram here, but basically you need two PLR-IRST injectors, injecting 50% of the fuel designed to optimize mixing and drive off the maximum fuel, 0.2 seconds below the lower meal. You then need further two RST injectors to hot reburn the fuel NOx, and need 0.4 seconds residence time above the lower injectors. The lower two-step meal with 30%, and then two directly opposed direct tertiary air injectors designed to give 0.7 lambda in air staging zone for 1 second's residence time. That should meet the stratified combustion gas and petcoke to minimize CO and NOx and reburn, maximize fuel burnout and calcination. The upper two-step meal above the tertiary air ducts with 70%, and variable orifice to stop the meal dropping through. With those circumstances for coal in an SLC or even an ILC, you should get down well below 500. And for petcoke, even an SLC, you should be able to get down to less than 500. So consequently, in conclusions, to get 500 at the stack, one needs a comprehensive understanding of process data on how NOx is generated in each individual calciner, the level of reburn and staging currently taking place by typical plot of stack against kiln back end. NOx, the level of NOx generated by the char, with the above and a detailed understanding of calciner design in terms of dimension modes, etc., plus TAD design and layout. 3, via our detailed fundamental knowledge on how to get reburn and staging with any fuel. Via the judicious application of Trie Smart Flow with a unique third-generation post-processor, we can achieve less than 500 in a calciner for petcoke or any type of calciner. However, I must remember the last words of the famous Gerard de Soot to myself on hot reburn when I was discussing it with him about 10 years ago. He said, reburn is like being on a tightrope, very good until you fall off. The line between success and failure is very, very narrow. Tree allows the plant to walk this fine line. That is the end of my presentation. Thank you for listening.
Thank you, Dr. Tom. Yeah. Thank you. Excellent presentation. I've in India right now using very large book, and I think it's a solution without going for SNCR, how we can actually the process improvement through which we actually reduce the NOx within the limits, because Indian standards call for the existing plants of 600, new plants of 500 is the regulation. Most probably the plants will be able to fulfill this requirement, both the current regulations and as well as the future regulations. Thank you very much.